Sagittarius A. At the center of the Milky Way, 26,700 light-years away, lies Sagittarius A, a supermassive black hole with 4.3 million times the mass of the Sun. Stars in its vicinity, like S2, whip around the core at thousands of kilometers per second, some reaching speeds close to 3% of light. Andrea Ghez, the UCLA astrophysicist who tracked these stellar orbits for over 16 years, provided the strongest evidence of its mass, earning the 2020 Nobel Prize in Physics. In 2022, the Event Horizon Telescope released the first direct image of Sagittarius A's shadow, confirming predictions of Einstein's general relativity. Spacetime here is so severely warped that light itself bends into chaotic paths, and anything crossing the event horizon becomes unrecoverable. TON 618, located 10.4 billion light-years away, is one of the most extreme black holes ever detected, with an estimated mass of around 66 billion suns. First identified during quasar surveys in 1957, it remains among the largest and brightest quasars known in the observable universe. Its accretion disk radiates with such intensity that it outshines entire galaxies, powered by matter spiraling inward at relativistic speeds. Estimate suggests TON 618 consumes hundreds of suns' worth of mass every year, releasing staggering amounts of energy as radiation. To observers on Earth, it appears as a pinpoint of light, yet its output is 1,000 times greater than the Milky Way's. The scale of TON 618 pushes astrophysical models to their limits, raising questions about how such monstrous black holes form. Planck scale. At the Planck scale, distances shrink to 1.6 times 10 to the power of negative 35 meters, a realm so small that current instruments cannot probe it. Here, quantum mechanics and general relativity both apply, yet their equations collapse into contradictions, signaling the need for a unified theory of quantum gravity. Spacetime itself is theorized to lose its smooth structure, becoming foamy as virtual particles constantly fluctuate in and out of existence. This chaotic backdrop makes predictions nearly impossible, since the fabric of reality no longer behaves as continuous. No experiment has yet reached this regime, leaving it as purely theoretical territory where new physics must eventually emerge. Big Bang singularity. Tracing the expansion of the universe backward leads to a singularity 13.8 billion years ago, where temperatures exceeded 10 to the power of 32 Kelvin, and densities reached levels that make all known physics break down. At this point, general relativity predicts infinite density and zero volume, a paradoxical state where time and space themselves lose meaning. The equations collapse under these conditions, showing the limits of both relativity and quantum mechanics when pushed to their extremes. Scientists use the cosmic microwave background, mapped in detail by WMAP in 2001 and Planck in 2009, as the best observational evidence of the early universe, capturing conditions just 380,000 years after the Big Bang. To resolve the contradictions, physicists proposed cosmic inflation, a theory suggesting that the universe expanded faster than light in its earliest fractions of a second, smoothing out irregularities without invoking an actual point-like singularity. Neutron star crusts. Neutron stars are the collapsed remnants of massive stars, only about 20 kilometers across, yet holding nearly twice the mass of the Sun. Their crusts contain matter so dense that a single sugar cube-sized piece would weigh 1 billion tons on Earth. Many neutron stars spin hundreds of times per second, their rapid rotation generating beams of radiation that sweep across space like cosmic lighthouses. Magnetic fields around them, trillions of times stronger than Earth's, can even distort space-time in measurable ways. Inside, pressures crush atomic nuclei together, until matter exists in states beyond anything reproduced in laboratories, challenging models of nuclear physics. Magnetars. Magnetars, first discovered through X-ray bursts in 1979, are a rare and extreme class of neutron stars, with magnetic fields measuring up to 10 to the power of 15 Gauss, about a quadrillion times stronger than Earth's. These immense fields twist and strain the star's crust until it fractures in violent starquakes, unleashing bursts of energy equivalent to 10 to the power of 15 atomic bombs in a fraction of a second. Such eruptions can outshine entire galaxies in high-energy radiation. While their magnetic influence is so intense, it could erase data from hard drives even 1,000 kilometers away. The Swift Observatory and other instruments continue to track these unpredictable bursts, which remain some of the most violent events in the known universe. Quantum vacuum. The quantum vacuum, often misnamed empty space, is in fact a restless sea of activity where virtual particles constantly pop in and out of existence. Even in a perfect vacuum, fields retain residual energy, known as zero-point energy, which gives the vacuum a measurable pressure. This effect was first demonstrated in 1948 through the Casimir experiment, where two uncharged metal plates placed close together experienced an attractive force generated by vacuum fluctuations. These results confirm that the vacuum itself has physical consequences, influencing particle behavior and energy distribution at the smallest scales. Some theories suggest that dark energy, the mysterious force accelerating the universe's expansion, could be directly tied to this vacuum energy. Dark flow. In 2008, astronomers analyzing data from NASA's WMAP mission identified a strange large-scale motion known as dark flow. Hundreds of galaxy clusters, some billions of light-years away, appeared to be moving at speeds of roughly 1,000 kilometers per second in the same direction. What made this unusual was that their motion pointed toward a region beyond the observable universe, where no data can be collected. According to standard cosmology, such coherent motion on these scales should not exist, as cosmic expansion should dominate cluster movement. This contradiction quickly turned dark flow into one of the most debated anomalies in astrophysics, with some suggesting it reflects structures outside our cosmic horizon. Alternative explanations, such as systematic errors or statistical chance, have not resolved the anomaly, and later surveys with Planck left the issue open. The persistence of dark flow as an idea hints that our cosmic models may still be incomplete. Cosmic strings. Cosmic strings are hypothetical one-dimensional defects in spacetime that may have formed during symmetry-breaking events in the early universe, with widths smaller than a proton, but lengths that could stretch across entire galaxies. Predicted by certain grand unified theories, these objects would carry enormous mass per unit length, warping spacetime so strongly they could lens background light into double images. Surveys have searched for their gravitational signatures, but no confirmed detection has yet been made. If they exist, cosmic strings would represent cracks in the universe's foundation, offering a rare window into physics beyond the standard model and inflationary cosmology. Gamma-ray bursts. Gamma-ray bursts were first detected in 1967 by the U.S. Vela satellites, which were originally built to monitor nuclear tests. These bursts outshine entire galaxies, releasing more energy in a few seconds than the Sun will emit in its entire 10-billion-year lifespan. One particularly intense burst in 2008 discharged an estimated 10 to the power of 44 joules of energy in mere moments, a staggering output that dwarfs most cosmic events. Lasting anywhere from fractions of a second to several minutes, they are thought to originate from collapsing massive stars or mergers of neutron stars. If one occurred within 6,000 light-years of Earth, its radiation would strip away our ozone layer, exposing the surface to deadly ultraviolet light. Information paradox. In 1976, Stephen Hawking proposed that black holes are not entirely black but instead radiate energy through what became known as Hawking radiation. This process implies that black holes can slowly lose mass and eventually evaporate completely, releasing their stored energy back into the universe. The problem arises because this radiation appears thermal, carrying no trace of the information about the matter that originally fell in. According to quantum mechanics, however, information cannot be destroyed, and its apparent loss breaks one of the most fundamental rules of physics. The contradiction sparked the black hole information paradox, which remains unsolved nearly 5 decades later. Quasars. Quasars were first identified in 1963, with the object 3C273 becoming the earliest confirmed example, located about 2.4 billion light-years away. These objects emit up to 1,000 times more energy than the Milky Way, powered by matter spiraling into supermassive black holes at their centers. As gas falls inward, it heats to millions of degrees, creating accretion disks that shine across the electromagnetic spectrum, from radio waves to X-rays. The energy output is so intense that any nearby planetary systems would be sterilized instantly by the radiation. Quasars serve as some of the brightest beacons in the universe, visible across billions of light-years and used to map cosmic expansion. False vacuum decay. False vacuum decay is a hypothetical instability in the Higgs field, the quantum field responsible for giving particles their mass. If the Higgs sits in a false vacuum rather than a true lowest energy state, the universe could one day quantum tunnel into a lower energy configuration. This shift would rewrite the laws of physics instantly, causing atoms, forces, and matter itself to lose their current stability. The collapse would spread outward at nearly the speed of light, offering no warning and no chance of survival. Particle physics does not rule out this possibility, and current measurements of the Higgs boson mass even suggest the universe could be metastable on cosmic timescales. While the probability is infinitesimally small in human terms, the scenario underscores how fragile our understanding of fundamental physics remains. If you enjoyed this, I'm going to be posting a lot here. I would greatly appreciate it if you could subscribe. Thanks for watching.